We will continue on with inductance today. We probably won't get through the AC circuits in class today, so I will be explaining those in the lab. Hopefully you've done the concept coach questions dealing with the AC circuits. For class on Wednesday, then we will be going over chapter 24 in its entirety. And that's the end of material for the exam 1 week from tomorrow. Yay. Because, we don't want to go too long with me not having any grading to do. That would be bad. Okay, so let's get into inductance again. This is not specific to inductors. This is something we've learned in the past, that power is I squared times R. Now, I'm going to introduce something right here that will help us for the lab tomorrow. The difference in AC and DC. So for DC, that means we have constant current, right? The D means direct or constant current. And we learned these equations for DC. Now, if we have AC is alternating current. Then we're going to have, and as far as you're concerned for this class, AC is always going to be sine waves, right? In real life, you can have all kinds of things that are variable that aren't sine waves. But for this class, it's just going to be sine waves. And so we would have something like, let's say the voltage as a function of time looks like this. So that's a sine wave. Now, if I have a resistor, what's the resistance? What's the current going to look like? If it's a resistor, how does voltage and resistance relate through a resistor? Ohm's law. So we have I equals V over R. So it's going to have the same shape. I put a different magnitude on it because, current is voltage over resistance, and we have different units. So the size is independent anyway. So if I take this and I calculate the power instantaneously at any instant is the current instantaneously times the voltage instantaneously. Right? That was our equation, that power is voltage times current. If it's DC, the average is going to be the same as the instantaneous. If it's AC, though, it's going to be constantly fluctuating. Because when current and voltage are both zero, what's the power? Zero. Right? So it's going to go down to zero at that point. But notice that if I have the voltage negative, what's the current? The current is also negative. So voltage times current, when they're both negative, what do you get for the power? Positive. So if we plot the power, so the power in watts, the power is going to go, okay, very nice drawing there. Okay, those are supposed to be all the same height. And it's a sine wave that's shifted, so the minimum is zero, and then it goes up higher. So the power using Ohm's law to substitute for I is voltage squared over R. So I plotted voltage squared. With all of this written down, it doesn't seem like I'm getting anywhere. What we design is we say, let us devise a system where we can use the same equation for the average power if it's AC or DC. So we want the average power to equal V times I. Now, if you look at my graph with the 3 different colors, what is the peak that I have up here? The power max, what's it equal to? Vmax, Imax. If it's a sine wave, where's the average for the sine wave? It's what? Right in the middle. So that means I can read from this and say the power average is equal to 1/2 Vmax times Imax. Now that's pretty simple, but that's not the same equation. And so what we do is we introduce a word we've used before, root mean squared. So I can put it this way as well, 1/2 Vmax squared over R. Well, what I can do is I can say, okay, Vmax squared is, the square of Vmax, very clearly. And if I take the average of V squared, the average of V squared is 1/2 Vmax squared. So the average of V squared is equal to 1/2 Vmax squared. And then I just square root it. And that's what we call the RMS. So VRMS is equal to 1 over square root of 2 Vmax, right? Because Vmax squared, when you square root, it just becomes Vmax again. And the 1/2 square root of 1/2 is 1 over square root of 2. And then we put that in and we say the power average is equal to VRMS squared over R, or VRMS IRMS. And so that's how we find the power through a resistor. Now I had to use Ohm's law for this, right? So the average power for a resistor is what I found here specifically. If it wasn't a resistor, this wouldn't have been correct. But for a resistor, the average power is VRMS IRMS. So when we start talking about voltages, like the voltage coming out of the wall here, the voltage coming out of the wall is 120 volts RMS. I ran out of space. So V wall is equal to 120 volts RMS. What's the peak voltage coming out of the wall? What's the maximum voltage coming out of the wall? If I solve this for Vmax, what do I get? So the peak voltage coming out of the wall is 169.7 volts. What about the minimum voltage? Okay, it's actually minus because it's symmetric about for the actual voltage. So it's going from, we round it off to plus 170 volts to minus 170 volts. What's the average voltage coming out of the wall? 0. That's why we never talk about the average voltage for AC signal. It doesn't really help us to know that the average is 0, right? We can't do any good, useful calculations off of that 0. So that's another reason we talk about the RMS value. So we'll talk about the RMS voltage, the RMS current, or we can talk about the peaks. We like to talk about the RMS because our average power equation stays the same. And likewise, Ohm's law, VRMS is equal to IRMS times R. Okay, now back to what was on here. Those are the equations for power. For a transformer, it delivers power, and you want to deliver maximum power. Now, if you have a power plant that is, let's suppose at the Oroville Dam, since it's in the news these days, there's a power plant there. And you want to get that power from the Oroville Dam over to Sacramento. How do you do that? How do Americans transport electrical power from the Oroville Dam to Sacramento? They go through power lines. So those power lines, we're going to have current going through the wires. The wires have a resistance. So we're going to have a power that's lost in the wires that's equal to the current of the wires squared times the resistance of the wire. In terms of current, how can I minimize the amount of power I lose? Do what? Well, if I put a high current, that power loss is proportional to current squared. So if I go higher, the power loss is higher. So instead of higher current, we want lower current. Well, how can we affect lower current? If we boost the voltage, if we make the voltage, let's say that we raise the voltage by a factor of 1,000. So let's suppose that we generated 120 volts. I don't think they do. But let's say we generated 120 volts, and we raise it by a factor of 1,000 to 120,000 volts. They actually raise it by more like 2,000. But just 1,000 because it's the easy calculation. We raise the voltage by 1,000 volts. What does that do to the current? It's going to decrease by the same amount because the transformer had the ratio of voltage and current such that you have ideally no loss of the transformer. So if I raise the voltage by a factor of 1,000, I lower the current by a factor of 1,000. What's that going to do to the power loss? It's going to lower by how much? By a factor of 1,000,000. So by raising the voltage a factor of 1,000, you decrease the power loss by a factor of 1,000,000. That's really appreciable. So that's why we have this system of using transformers to raise voltages and then have high voltage lines going across the country, then lower the voltages when it gets to our neighborhood for distribution to the houses. Because we have less power loss in distribution. That was the point of this slide. American scientists, it's always good when you can say an American scientist because, in the history of science, there's not that many that were American scientists. Joseph Henry was the first to wrap insulated wire around an iron core to make an electromagnet. I put it away, but like that ring tosser thing I had. And he suggested that by putting a current through it, you can get a voltage, which we then call a self-inductance. Remember, we talked about mutual inductance last class period. Because of this, we named the units of inductance after him. So the units of inductance are Henrys, named after Joseph Henry. So this is what inductors look like. I know this is a poor quality picture. What do all these things have in common? They're wires wrapped in loops, generally around a piece of iron. So like in this one here, there's an iron core inside there, and then you have wires wrapped around loops. Here you have the wires are wrapped around this way, around the iron core. Here you have the iron core like that with the wires wrapped around it. Those are how inductors are made. Very simple design. Now let's talk about this inductance and how it's useful or what happens with an inductor. So there I've drawn my hand-drawn inductor. How does an inductor look compared to a resistor? The difference is these have curves. That's why you have to be careful and make sure you use straight lines with angles at the tops and bottoms of your resistors. Because inductors, curly lines that otherwise pretty much looks the same. So if you're sloppy, they could look like the same thing. This is supposed to be showing loops. So that's an inductor. And I have current going through it. If I have current going through the inductor, we know that that's going to make a magnetic field inside of the inductor. And we've already learned the equation for that magnetic field. The magnetic field inside of the inductor, if it's air-filled, it's mu naught times the number of turns divided by the length, multiplied by the current going through. And of course, I did this actually on Friday for the transformer version. So what's the flux then if I have that magnetic field? Okay, dot product of the area vector is correct. The flux is the magnetic field dotted to the area. Well, the area is going to be, you take a ring, the area is pointing this direction, the same direction as the magnetic field. So, well, same direction or opposite direction, depends on which way it's wrapped, if it's the same or opposite. So it's going to be, for the flux, mu watt times N over L, current times the area. And then you see we have this definition of inductance that the number of turns times the flux is equal to the inductance times the current. I actually think of it a different way. I think of it as that way. It's written a little differently there because I wanted my, I forgot. It's not Li, it's delta I over delta T. I made a mistake there. The induced voltage is minus L times the change in current over change in time. Because I just have a divided by delta T on both sides, you can see that the two equations are equivalent. So let's just stay with the top one because that's one the textbook uses. If I want to calculate the inductance, then I'll just take this here, plug it in, whoops, missed. Plug it in there, and I have well, clearly we can cancel the I on both sides. And we have the inductance, the physical inductance, mu watt N squared times the area over the length. I don't think I made any mistakes. Well, actually, yeah, it looks different on the coming up pages because they put, instead of area, they put pi r squared. Because if it's a circular coil, the area is pi r squared. So I was looking, I'm like, that's not the way it. So that's the physical inductance. Just like with the capacitor, we could come up with the physical capacitance based on the area of two plates and their separation. For an inductor, we can come up with the physical inductance based on the area of the loops, the number of turns, its length, and of course that constant mu watt. What is that mu sub zero? What does that mean? Okay, it's the permeability of free space, which basically tells us how magnetizable a vacuum is. Well, what if I put iron in instead? If I put iron inside of my loops, what's that going to do? It's going to make it much more magnetizable, and so that mu aught will become just mu for whatever the material is if we put something like iron in there instead of having just air core. So the units, the name of the unit is the Henry, so 1 Henry is equal to, and if we look at how I calculated this, the inductance, actually, come up here, the inductance is going to be units of magnetic flux divided by units of current. Magnetic flux is Webers, current is amps, so that's the second one, Webers per ampere. And then going further, you can get it into volts times seconds per ampere. Basically, I just use the Henry for inductance, and I trust that if I use standard units, what's the standard unit for capacitance? The farad. If I use farads for capacitance, if I use ohms for resistance, if I use Henrys for inductance, volts for my voltage, amps for my current, the units will work out, and I kind of just trust things because when we get to the Henry, I start getting confused about the units myself. So you've already seen this equation. There it is, except for I guess I had a minus sign, forgot to carry the minus sign. So the relationship between the voltage that's induced on an inductor due to current changing is shown. Now this is an important thing. If I have current, if I start with no current and I start putting current through an inductor, what's happening in that inductor? You go from no current to current, what's it doing? Creating, it's not creating a vacuum, it's creating, the one I was looking for was a magnetic field. But in creating that magnetic field, it's going to induce the electromotive force. And so what we're doing is we have the current creates a magnetic field, and that magnetic field, because we have a changing magnetic flux, it induces an electromotive force that's opposing the change. So if the current is increasing, then I'm going to have a voltage that's going to try to oppose that current. So I'm going to have a voltage that's going to make it so the voltage is ending up going from positive to negative. It's losing energy. The energy is going into creating a magnetic field. So that's what an inductor, that's how we use it in a circuit. It's going to create a magnetic field and store energy in the form of a magnetic field. And then it will give that energy back, just like a capacitor gives the energy back. An inductor doesn't use power or doesn't use energy. The average power for an inductor should be 0. The average power for a capacitor should be 0 because they store energy and give it back. So in our circuits, that's going to be an important thing. So here's the equation. Okay, there's another. This is the form that I did, except for you can see this right here. I just put area for what's inside the bracket or the parentheses. What's the difference in those two is they used here the number of turns per unit length. So you have a choice of which variables to use, but it all comes out to the same answer. How to calculate the physical inductance. Now, because it stores energy, sign conventions. Remember with a resistor, if I have a resistor and current's going like this, which side is positive? The which side? Okay. I thought he said the plus side. I was like, well, yes, that's true. Good call there. Okay. Why? Because resistors always absorb energy. With the inductor, if the current's increasing, then it's the same. If the current is decreasing, it's reversed. Well, when we start doing circuits, we're going to use this because we assume a positive change. If it's a negative change, that's going to put a negative sign in our work, and it's going to change the direction for us. So we basically follow the same sign convention for drawing things. But remember, that's the direction of the voltage only when the current is increasing. When the current is decreasing, it flips to the other direction. In case people, how many people bought it when I said that the average power for the inductor should be 0? Okay, a small group. A number of people didn't raise their hand. Let's go back and just review that real quick. We have for an inductor, the EMF is equal to minus the inductance times the change in current over change in time. So if I have a sinusoidal current, if my current goes like this, then my voltage is going to be minus the slope of that, right? Since delta I over delta t is the slope. So I have places where the slope is 0. Which places is the slope 0? I marked places where it's maximum and 0. Where are the zeros? When the slope is horizontal, which occurs at the peaks. So if I'm going to plot my voltage is going to be 0 here, 0 here, and 0 here. And the slope is positive here. Putting in that negative sign, it's going to be negative. So my voltage is going to be going like like that. It's a sinusoid, but it's offset by 90 degrees. Now, if we look at this, we have that offset, and the question is, which color or which symbol, current or voltage, reaches its peak the first? Right? At which one will be the first one to get to its peak? Okay, we have people that said current. So just to make sure everybody understands why it's current, because they're correct, if we put an axis on here that goes like this, at time equals 0, the current's at its peak. And you have to get out here to this time before the voltage is at its peak. And so the, actually, did I do this right? Minus, plus, minus. That should be right. Somehow now I'm feeling really bad because the mnemonic is Eli, the Iceman, and somehow I have it backward. That's impossible. Anybody here recognize that reference? Not a one? Me fail English? That's impossible. Ralphie Wiggum? No. Okay. Maybe it's a Simpsons episode from too early for you guys to have seen it. Okay. This here's our mnemonic to remember which one reaches its peak first. And Eli means the voltage in an inductor leads the current, which means the voltage should hit its peak first. I don't know how I could mess this up, but my picture shows the current reaching its peak first. I will have to go back and revisit this. I mean, obviously, I have a minus sign here, but I think it's supposed to be there. So I will have to come back to revisit that before lab tomorrow. So in lab tomorrow, I'll get that straight. But the reason I did this was the power. If I'm going to get the power, I have to multiply power instantaneous is equal to the voltage instantaneous multiplied by the current instantaneous. And so now if I multiply those two together, you'll notice that from the places that I have the green line, I have a positive voltage and a positive current. So that means voltage times current is going to be positive. But then if I change to purple, from here to there, one's positive and one's negative, which means I'm going to get a negative power there. And then going back to green, they're both negative, which means a positive power. Going back to purple, one's positive and one's negative. If you plot the product of these two together, you'll find that you have the power is going to go like that, a sinusoid centered on 0. So what's the average of a sinusoid centered on 0? 0. So the power average is equal to 0. The power moves positive, negative, because it's storing energy and then it's giving it back. So that's how you can see, yes, the average power is 0. The instantaneous power can be both positive and negative. Okay, our first clicker question. Computer, come back to me. Okay, you can't answer yet. The computer went on vacation. Now you can answer. What is the unit of inductance? Okay, everyone has answered. We had 19 that said Henrys, 2 that said Faradays, and I am going to call on 6 people. Carrie, what type of thing has units of ohms? Okay, resistors. Now, Carrie has a little more knowledge than other people here. You've taken the circuits class, right? What else do you have besides resistors where we use units of ohms? And impedance as well. Now, impedance is a catch-all phrase that includes reactance and resistance. Reactance also has units of ohms. Okay, next up is James. What has units of coulombs? Charge, right. There's no explanation here. It's just a... Do you remember what has the units? Next up is Jerry. What has units of Faradays? Capacitance, excellent. Actually, I said I was going to call on 6 people. I'm only going to 5 because we all know what has units of Henrys? The inductors. That was the question. So, Larissa, what has units of... Oh, wait a minute. We're done. This is on clerks. I don't know what has a unit of clerk. Clerk was James Clerk Maxwell's family name. Maxwell was an additional family name that was added to it. And so I put James Clerk Maxwell's 2 last names there. I should have paid attention when I said how many I was going to call. Okay. Now, I've talked about inductors store energy. And I've been going through the power equation. Power is voltage times current. Now, this here, we're going to do a hand-waving integral, if you will. We are going to add up the total energy if I have a current that increases with a linear fashion and store energy in an inductor. So I guess I should have read this all for you. You're linearly increasing the current from 0 to I in a time capital T. So if you do that, you can calculate the average power is going to be the initial power plus the final power divided by 2. And so the initial power is 0 because you start with 0 current and a voltage of 0. Your final current is 1/2 EI. Why was it important that I have a constant increase? Oh, excuse me, that's not the final. The final is EI. So P initial equals 0. P final is equal to EI. Why is it important that it was increasing linearly, that the current was a linear increase with time? It's right here. Why is it important that it was a linear increase? If it's linear, then what does it tell you about the voltage across the inductor? It's constant. We have a constant voltage and just a changing current. If the rate of current was changing, then we'd have a changing voltage and changing current, and we couldn't do our hand-waving integral. We would have to do a real integral. But as long as we have a constant increase, then we just have the change in current over the change in time is equal to the final current minus the initial current over the final time minus the initial time. And so the voltage is minus L times final current over total time. And so we can say the average power is going to be this final power plus the initial power divided by 2 because we had a constant increase. So that's going to be, well, equals 1/2 of now notice I have a minus sign and that minus sign disappeared. Right, minus sign here, no minus sign in there. So that's our average power. I made a mistake here. Right, this was not a capacitor, it was an inductor. So the potential energy is going to be the average power multiplied by the time that I had this power being stored. And so that's just going to be multiply the T. So I had 1/2 Li squared over T multiplied by T. And we see that gives us the potential energy stored is 1/2 the inductance times the current squared. That's very similar to what we found for the capacitor. The potential energy stored in a capacitor was equal to 1/2 CV squared. So I've said the capacitor stores energy in the form of an electric field or a charge separation. Well, here you could say, well, it's also a voltage difference because of that charge separation. It's two different ways of talking about the same, or three different ways of talking about the same thing. The inductor is storing an energy in the form of a magnetic field, or you could say it's, well, because of the current. Two different ways of talking about the same thing. But we're going to go a step further, because next chapter, which happens to be Wednesday, we're going to talk about the energy in an electromagnetic wave. And so we're not going to have an inductor or a capacitor. We're just going to have electric fields and magnetic fields traveling through the air. And we want to know about the energy in these fields. So if we substitute the equation here for the inductance in the inductor, then we can put the potential energy stored in the inductor, 1/2 Li squared is 1/2, and this right here is the inductance. And then say, but wait, the inductor is a cylinder with area of pi r squared and length L. So let's calculate how much energy per unit volume. Because when we get to electromagnetic waves and we have electric and magnetic fields out in space, we're going to care about the energy per volume. So we just take this potential energy and divide it by the volume. And so notice it's a lowercase u to say that it's the potential energy per volume. And then just cancel out. And we have the potential energy is 1/2 mu watt n squared I squared, or there is a simpler way of writing it. It's the magnetic field squared over 2 mu watt. So the energy density, the energy per unit volume that's stored in a magnetic field, we did this with an inductor, but it turns out it's universally true, is the magnetic field strength squared divided by 2 times the permeability of the material within which you have this magnetic field. So this is going to be important to us when we talk about the energy in an electromagnetic wave. We can calculate the energy density stored in the magnetic field. Now to LR circuits. What does L stand for? Inductor. And R, resistor. So LR circuits are circuits with inductors and resistors. Now this picture shows, what's that? Okay. If you want it to be anal, it's a cell. But they use the symbol for cells for batteries, and they put the B there, you know they meant battery. We have a switch, so we can switch on the current. We have an inductor, and we have a resistor. Right now, the switch is open, so how much current is flowing through the circuit? None. When I close that switch, what's going to happen? Okay, current's going to flow. Now, there's an important rule in capacitors. We said that you can't have a discontinuous change in the voltage on the capacitor. The voltage on the capacitor has to do with how much charge you have on the plates. And you can't go from no charge separation to a large charge separation, right? The first electron has to cross, then the second, then the third. So with the capacitor, we could not have a discontinuous jump in the voltage on the capacitor because that would have meant a discontinuous change in the charge state in the plates instead of charge flowing on the plates. With the inductor, we have a similar rule. we can't go from zero current to some random current. We can't have a discontinuous jump in current because that current is building the magnetic field. And you can't just go to a large current from nothing. So the current has to change continuously. So there is no current before I flip the switch. When I flip the switch, initially the current's zero, but it starts to flow. And so I'm going to have a current start to flow. And when there's no current, what's the voltage across this? When there's no current, the voltage across the resistor is zero. So when I first flip the switch, I'm going to have a voltage jump to the full battery voltage across the inductor. But then as current flows, that inductor is going to start building its magnetic field, and it's going to have a voltage that's opposing the flow, decreasing the voltage across the resistor, and thus dropping the current. So here's the rule I just talked about. Current can't change discontinuously. It has to be continuous. Let's just get to it. Here's what's going to happen for the voltage across that inductor. It goes from zero to jumping up to the full battery voltage, and then it drops down. Does that look like a familiar curve? It should, because it's exactly the same relationship as we had before. The voltage across the inductor is equal to the voltage across the battery times e to the minus t over tau, just like before. But now tau is not equal to RC, it's L over R. So the time constant has L on top instead of C on bottom. Or, well, actually it was RC. Has R on bottom instead of on top, and the L stays on top. So this is our time constant for the RL circuit. So it's not the RL time constant, is it? It's the L over R time constant. This here is showing the opposite situation. The current is equal to I max times 1 minus e to the minus t over tau is the easiest way to write that equation. The equations that we use for RL circuits are exactly the same as the equations for RC circuits. The only difference is tau has a different definition. And so if you know how to do one, you can do the other. Why do they have the same functions? Because the rate of change is proportional to the value. We have rate of change proportional to the value that introduces this logarithmic shape. I'm actually finishing early because this is pretty much where I intended to end off. Right there's the tau that I've been talking about in the equation for the voltage. An inductor in an LR circuit stores energy and then returns it. How does it store energy? I didn't want to put this the instant after we talked about it, so have to remember for a few seconds. Which so far 11 people have. All righty. Ooh, somebody changed to the right answer at the last second. 0, 20, 1, 0, 0, 0. Okay, now once again, I'm going to go through people. Brandy, what stores energy in the form of an electric field? Okay, capacitor stores energy in the form of an electric field. I know you're like, whew, today is not as hard as it could be. Don't have any explanation. Okay, since 20 out of 21 said magnetic field, good. You remembered that. Inductors store energy in the form of a magnetic field. Okay? I won't ask anyone C. An electromagnetic wave stores energy in the form of electric and magnetic fields. That's the one that one plays into. And so you have to answer both, and it's just kind of silly. Caitlin, what stores energy in a chemical form? Oh, yes, Caitlin Toy. Yeah, based on where I was looking.
I'm not really sure. I'm a little confused.
Okay, this was actually one of the questions that was on the last test. We had the capacitor versus the battery. The question was, well, there were other ones, but I don't think anyone answered the other ones. Like a transformer was an option for it as well. But a battery is a device that stores energy in the form of a chemical reaction. So you have reactants, and those reactants will undergo the reaction until you build up a big enough voltage difference, and then it stops. And then as soon as you connect a circuit to it, then the voltage difference drops, and the reaction picks up again until you've used up your reactants. So a battery is storing energy in the form, I guess I should write out the answers here. This one was capacitor. This was inductor. This one was a battery. Now, these last two, you could come up with answers for the last two, but gravitational form, something stores energy in gravitational form. Just give me an example of something that does that. If you can come up with something that's useful, that's even better. Calling on Aaron.
When creating a potential energy difference,
well, what stores potential energy? What stores gravitational potential energy? Think of something where we can use it, like I mentioned earlier today.
like a spring, maybe?
Okay, well, a spring does that, so that's a fair answer. What I was hoping for was somebody to recall me talking about the Oroville Dam. The Oroville Dam has a hydroelectric plant. How does that work? You have energy stored in gravitational potential energy of the water. You let the water flow, it converts the gravitational potential energy into kinetic energy. That kinetic energy then turns a generator, converting the kinetic energy into electrical energy. So all I was asking was what stores in gravitation, which is why your answer was correct. There are places where they actually have too much electricity during the night, not enough during the day. So what do during the night? They have a system built where they pump water up to a lake at the top of a hill. And then during the day, they run the water down from the lake to turn a turbine and get electricity out of it. It's a way of storing energy somewhat efficiently. I say somewhat because, of course, evaporative losses are not there. Nuclear form. Anyone want to just shoot one out there? Isaac.
Nuclear reactors?
Yeah, nuclear reactors. Seem pretty obvious, right? Nuclear reactors are taking the energy stored in a nuclear form. We haven't learned about nuclear science yet, but we have the nucleus of something like uranium-235 is unstable. It's in a higher potential energy state and it can fall to a lower state. So it's just like if I were to take her phone and somehow magically get it balanced here. It's theoretically possible, right? If somebody breathes on it, it's going to fall down. That's what the nucleus is like in these atoms. And what they found you can do is you can force them to fall down. If you hit them with slow-moving neutrons, you'll make the nucleus get a little excited, it'll absorb the neutron, go to a higher energy state, and then fall down to the lower energy state. So it's kind of like you have a bunch of things stacked up, and you shoot them with a little BB, it falls over and gives a whole lot more energy than that BB that hit it had. And so that's using energy stored in nuclear form. Okay, I actually do have more here, but I'm now out of time. I just have solving problems. So I'll see you in lab tomorrow.